So in this video we're looking at nonlinear graphing. We've previously seen how to graph and how to find the equation of a line, which is the relationship, mathematical relationship. So in this case we're looking at, first of all, to identify the general relationship. So there are various shapes of your graph. You actually have to plot the first graph, and there'll be a curve to it or something like that. So a linear graph is easy to deal with just a straight line linear. That tells us that the y, whatever's on the y-axis and whatever's on the x at y is proportional to x, directly proportional. And we don't have to worry about that. We can just do our rise over run, calculate our gradient, and find an equation. But if we have curves, it can get a little bit tricky. If we have a curve like this that shows that y is proportional to x squared, this is like the half of a parabolic relationship. We can also have a graph like this, and that one gets a little bit trickier again. This is y proportional to inverse of x, or y proportional to the inverse of x squared. Now for this one, you don't know how you transform the data until you try it out. You might be able to work out some things from equations and other information from the context of where you've drawn the graph, but otherwise you won't know how to transform it. So we'll get to transforming shortly. It's worth replaying this video to put it into context again afterwards. So there's another shape that I'll give you, just a general shape, and this is, I should note, is particular for level 2 physics and level 3 physics, and does not include complex relationships like logs. There's this shape here, which is y is proportional to x square root of x. Okay. So if you're at level 2 physics or level 3 physics, it'll be in studying NCA in New Zealand. It'll be taken from one of these relationships. So what you have to do is look at the shape of the graph, identify the relationship. That tells you how to transform your data, and I'm going to show you how to transform your data right now. Okay, so your set of data, we'll use an x squared set of data. So here's x and here's y. We've set x to be this. I'll use a straight, for example. 2, 4, 6. Oh wait, no, is that going to work? Yep. 2, 4, 6, 8. Y is going to be 8. 32. I might have made myself difficult on this one. 72. 128. Okay, so I'll tell you how I got this so you know where I'm coming from. The x values, I've squared them and then doubled them. I could have done 1, 2, 3, 4, 5, 6, 7, 8 as well, but I've just given you 4 values. You should really have 5 values for a graph, but that's not the point of what we're getting at here. If I graph this, I'm going to find it has a square relationship. So what I'm going to do, and remember y is here, x is here, what I'm going to do is I'm going to square all of my values on this. So whatever the the same relationship, whatever the relationship the shape tells us that relationship is, we do that operation onto the x, or the independent variable. So we're going to have a new set of data, and I'll just put it over here for x squared, which is going to be 4, 16, 36 and 64. And you can see already that the numbers here, 4 is half of 8, 16 is half of 32, 36 half of 72, 64 half of 28, 128. So you can see that I've squared it and doubled it. So now I've squared my x values, and this series with this series actually makes a linear or a direct proportional relationship. So we will regraph that. Okay, so we're regraphing, and we'll just pop that in over here. Regraphing that, and we're going to find that it is a straight line. I'm not going to do all the points, but this axis is still y, so no change with that data. We've used that same data there, and this axis we just label it as x squared and pretend it's just the same, and we use that set of data there. Okay. Now we proceed as we did before in the linear example, and we find the equation. So to do that, we need to do our rise over our run. dot all the way back there to find whatever the y change in y is. Come down and find the change in x. So your rise over your run to find the gradient, which is the m value in y equals mx plus c. You look at your intercept. If there is an intercept, that's going to be the c value. Then you form your equation. Y equals m. In this case, though, x is actually x squared, so we have to put x squared in there plus c. So if this value here was 1 over x, in place of x, we'd put 1 over x here. If this value was square root of x, we would put square root of x in here. Okay, so I'll do another example on a future video. Hopefully I'll have time to get around to that in the near future, which will be a different one so you can see how that works. But you pretty much just form that graph. Maybe I should do a quick example with numbers in it. I think that's a good idea. We'll do a quick example with numbers in it. And I'll try and use real variables. So if we have the length of a pendulum and the period, the length is measured in meters and the period is measured in seconds, and let's say this is going to be really wrong and really rough, but we'll say our length can go 1, 2, 3, 4, 5. This is not going to be nice at all. Okay, I'll just very quickly do some calculation. Well, square root of 1 is 1. Square root of 2 is 1.4. I don't know the square root of 3, so I'll just quickly pause and get my calculator out. This is 1.7. Square root of 4 is 2. Square root of 5 is 2.2, and they should all be to the same number of significant figures just to make it nice. Anyway, so this data will produce a square root relationship. I don't actually need the data at this point, but we draw a graph of that. We should get a curve. Okay, so the curve tells us that L is proportional, change that, T is proportional to the square root of L, because L is our independent variable, which we'll put down here, and T is our dependent variable. Okay, so what we're going to have to do is square root our L values because L is on that axis. So square rooting the L values gives us this same set of data. Okay, because that's how I got that data. Keeping it really simple. Okay, if you're confused, you'll have to re-watch and think about it and try some examples yourself. So you get a straight line, T and L, and you find you're trying to find the gradient of that to get to the equation. So you might find that the gradient is, let's just say it's 2.0. Okay, I made that up. I don't think it will be that, but let's just say it is. That's m equals 2.0. And seconds, this is square root L. And just a good point, our units are going to be square root meters. We can't ignore the units that have been changed. And if we're looking for the units of the gradient, it's going to be the rise units over the run units. So it's going to be seconds over square root meters, which starts to get tricky. But if you just put the rise units over the run units, put brackets around them if they look a bit scary, around each individual part, then you generally won't go wrong. And we're going to say the intercept is 0 in this case, just to simplify our equation. So it has to be of the form y equals mx plus c. C is 0, so we're scrapping that, so it's just y equals mx. In this case, y is t, m is 2.0, and x is square root of L. So that's our equation. That's how we get our equation from using this process. Okay, replay the video, watch it over again, try some examples of your own. I might be able to upload some sample data for you to have a go at. Yeah, lots of practice. Ask questions of your teachers. Feel free to email me if you have questions as well, and I can make a video if I get enough emails of the same question.